Hello, good afternoon. Welcome to my stream. It's another Sunday. We're here ready to do compilers in Gleam, as I sometimes do right before the stream because I don't use this computer that much during the week. Got a work laptop that serves my purposes for weekdays. I decided to update Homebrew and it's taking forever. So we will hopefully be able to get that to finish, and then I can finish my other updates and we can get going. Last time we just to recap, we implemented some new intermediate languages. So we created the elif language. So this is the Lisp-like language with if and true and false in it. And we implemented some passes in our compiler. One that turns the and the or operators into short-circuiting if statements. And this pass was called shrink, and it was an effort to make the constructs that we use in the lower or less capable intermediate languages, and ultimately in x86 assembly, make those constructs simpler. And so we don't have to be concerned with having more complicated constructs down at that level. So we were about to take on the Uniquify pass and updating it for its new language that it supports. And if you recall, hopefully from previous streams, the Uniquify pass was basically letting you shadow variables. So it makes unique names for all instances of variables. So there's sort of like a renaming with a suffix, and then adding that suffix to further references toward that variable. So if you have a let of binding x to some value, and then inside that you reference that binding, but you also rebind x in some other expression, then you get the possibility that you would lose that if you didn't rename them. So this is making sure that they get unique names in all instances of the expression. Okay, so we are, hopefully my brews update is nearly ready. It is updating a bunch of things that I don't use anymore, unfortunately. So I'm going to have to get that fixed. All right, we'll hide the shell for now. So we were looking at entering this Uniquify pass. So it has this Uniquify exp function, which we implemented last time. But now that was over the lvar language. And remember that the lvar language didn't have if, and, or, not, and Boolean types. It was only integers and expressions over integer types. So what we need to do is to change this lvar everywhere to elif. And I'm tempted to just blanket replace that everywhere. That might be the easiest, not in the entire project, but just in here. We're going to replace with l_if. And let's replace all occurrences. And now we have, as we expected, oops, didn't mean to close it. As we expected, we have a compiler error here because we didn't cover all of the branches of expressions. And what they're saying here is, let it handle Boolean constants and if expressions. So let us look into that. we can just add them at the bottom here. So let's see if the assistant will add them. Okay, so it has added all of the other primitive operations, which is good. We've added bool, and that's a constant. So let's move that up to the top of this, next to the variable and the integer constants. Okay, and then yeah, so the only things that this is really concerned about, other than recursing into these internal expressions, is variables. So getting the variable out of the nested environment, and then let, which is transforming the variable in the binding to one with a counter. So what we will do, because if is a top level expression, let's move it after let. Okay, and then this is the condition and the if true and if false. So in here, we basically need to do something like this. Yeah. So let's do C1, counter 1, uniquify expression of condition, env, and counter. And then we'll thread that through. We're going to do T1, counter 2 is uniquify expression. Remember, we're not introducing any variables here, so we don't need to modify the env. It should be, it should already be there. So we'll do process if true, counter 2, counter 1, sorry. And this will only increment that if there are let expressions down inside those branches. Now technically they won't conflict, but following the pattern that we did everywhere else, I think it's just smart to thread that through like we did for all the other expressions. So if false, env counter 2, and then what we're going to return is if C1, T1, F1. So we've transformed those inner expressions, and then our updated counter for unique indexes, unique suffixes is there. So we can do basically the same for and, comp, not, and or, right? And we're not changing the semantics of any of these operations. We're just making sure that they are following the pattern that we have in the rest of this. So let's get A and B in here, and this is and this will be pretty much the same for these other things. And here will be comp A1 B1 op, and we don't need that, be not A1. And finally, or let's move this up so it's next to and. Oops. Move this, let's get spaces in here. And this is basically the same as and. Oops. Okay. A and B and OR. All right, so we need to handle bool. Honestly, this is not going to change anything. Just like int didn't change anything. Because that's a constant expression. Okay, so now, of course, our tests are going to fail because this needs to be using the elif language. And then let's run that without making any changes to the expressions in here, and then we'll add some more tests that cover if and or etc. and comparisons and so forth, so we can get more coverage. Hey, we're done. Cool. Okay, so let's run Gleam test, and I think I need to update my package versions. Okay. Because they changed. Okay, so what's wrong here? So this will not compile right now. I think we're going to just comment those out because we haven't handled the other passes, right? And then we'll change this to elif. Okay. All right, did I not get Gleam updated? Which Gleam? Is it in Homebrew? Yes, it's in Homebrew. Okay, so is really complaining about that. Okay, so we're going to have problems with these other passes because their types aren't going to match up here. Okay, let's restart the language server. Some of them are calling Uniquify. Where is that? Line 58 here. Okay. Unfortunately, I think I'm going to have to, until we get all the way down to the bottom, let's just find everywhere that's referred to in the project. So we expect it to be in there. We expect it to be in here. In this test. Okay, the Uniquify test, yes, I completely expect that. I think it's just this one test. So I'm going to comment that test out and we'll go back and fix it. Here. Let's actually put a to-do in here. And we'll comment out the contents of it. That way this that's fine. Okay, so the one failure is the to-do. That's to be expected. That's fine. I don't actually mind. And we'll want to reevaluate whether this test is actually meeting our needs, I think, because this is I'm going to make a stupid assertion there so that it passes and stops a warning. I think the issue there was like we wanted to express something in lvar that I didn't know what the output would look like for cvar, right? Because we're using select instructions creates an x86 program, x86 var program, and we haven't gotten to that yet. Okay, so I think this will resolve it for now. And then we get to go into remove complex operands and explicate control. And then there's discussion about jumps and so forth. Go-tos. Okay. All right, so I think we accomplished uniquify expression. Updating this. Our tests still pass. Let's add some tests to cover if statements. So let's come up with some examples. We want, say, let's do if. And then we need, let's do another let expression. Okay. So this should come out to be basically the same thing, but we'll see this will be x.1, right? And because of the order of evaluating the branches, that'll be y.2. So let's look, so uniquify if test. And this needs to be public, sorry. So we'll make a program. And it's going to be if, let's get if comp less than, what else do we need? Got plus, we got minus, okay. Okay. So we're going to do prim, let's be comp less than int 5, int 2. Okay, there's our silly test. Then we're going to have let, and that's going to be x is int 42. In prim plus var x int 10, and then the other branch is going to be let y int 30 prim of minus var y int 5. Okay, so we're going to say p is that, and then we're going to copy this, and we're going to say p2 is this, and we're going to renumber this like we did in the example above. So those get suffixes so that they're unique. And we'll say p uniquify should dot equal p2. Okay, and it reformatted for us. So let's run that test real quick. And that passes. Oh, that's fine. Don't care. Okay. Let's do one more. And I'm thinking of one that has internal Boolean operations, and it's like and or not, or has a if inside a let. That would be interesting. Let's do let x1. Actually, let's do x is if. We're going to do greater than or equal to read is 10. Then we'll bind x to true. This is a dumb one. Or false, because we could just substitute comp. Maybe let's reverse it. Okay, so then we bound x to that expression, and then we'll do if and x and true. I don't know. Or this is dumb. Then we'll say 5 or 10. So this will demonstrate if in the bind inside the let and variables inside the condition, also inside a Boolean operator. And I don't really want to get too picky about this because it's a very straightforward pass. You could imagine a useful way to test some of this might be to create a property test which generates valid syntax trees. And then the property is that for every binding, it gets an index, and that for every variable reference in the tree, that there's also an index to it. You would want the property to be tighter than that. You want to make sure that you don't create variables that are never used. So like the generation would need to be somewhat stateful. But that's a problem for another day. So we'll just do this test and then move on. Boolean ops test. All right. Okay, so we've got a let. It binds to an expression of if, and this is primary. This if its condition is primary, it has a comp of greater than or equal to, and then it has a primary read, and then it has int 10. Okay, and this is returning bool false or bool true. Again, it doesn't have to make sense. It just has to be correct from the perspective of our syntax and our transformation. Okay, so then we're doing an OR with var x, bool true, and int 5, int 10. So we need to import OR and bool. And it reformatted our stuff. We need read. And we need GT. Okay, so then let's copy this. We'll say P2, and we're going to renumber the variables in there. Okay, and then P uniquify should equal P2. Okay. And let's run that test. Okay, so we're still passing. I didn't expect that not to pass. Let's go ahead and add, let's update that. Upgrade dependencies for Gleam 1.11. Okay, and then we are, this is chapter 4.6. Yeah. Update uniquify. Cool. Okay, and I'll go ahead and push that. Now we need to go into remove complex operands. So let's jump over there. And let's start by reading. The output language of remove complex operands is elmon if. So we need a new language. It's basically a copy of elmon var, and we add the if stuff. So they're saying monadic normal form of elif. Right, so if I recall correctly, we're going to elmon if. If I recall correctly, what this did was pulled nested expressions and lifted them up into let bindings so that you could do simpler operations, and this prepares us for sequencing, the kind of sequencing you would do in the C-like language, where you do one operation and assign it to a variable, one operation, assign it to a variable, and so forth until eventually you get to return. And I think that's what this does, if I recall correctly. So you can see here we have a couple examples. So this plus 42, or like adding 42 to negative 10, the negation of 10. This introduces a variable to which you bind the negation of 10, and then you substitute that variable in the original expression. So let's read what they have to say. So we're going to make, let me duplicate this file, and we're going to call it elmon if. Okay. And Right, and so the difference here is that if you look at elif, arguments can be full expressions, but in elmon, arguments have to be atomic. So, there has to be a lot of unwrapping of things. Let's read. The output language of remove complex operands is the monadic version of elif. A Boolean constant is an atomic expression, but the if expression is not. Okay, so we can add bool here, value bool, as an atomic expression. All three sub-expressions of an if are allowed to be complex expressions, but the operands of the not operator and the comparison operators must be atomic. Okay, so if can contain expressions, but if you're feeding it things like and or not, etc., those have to have atomics. The other thing that's going to be challenging here is that I think what we want here, I would love that we're not type checking at this level. So I guess we should probably assume that it has been type checked at this point. So we don't need to concern ourselves about whether the expressions that we're putting inside Boolean operators are Boolean typed. The other option is that we do something like bool, which is just bool, and then we don't put it in there. However, variables can be Boolean. So like, yeah, I think the first way is fine. If we are able to make the assumption that we've already type checked the expressions that are fed into a Boolean operator, at which point we know the variable is a bool type, or it's an atomic like constant and it's bool. So let's see what they do down here. Yeah, they're just going prim not or prim comp into atomic. The other thing is that I think that this comes after shrink. So we don't actually have and. We only have if, which is really interesting. So this makes this language a lot simpler. Remember they were talking about that earlier. So not becomes a primitive operator. And we need comp, which takes an op, which we'll have to copy from elif. And it takes an atomic, B, an atomic. And then there's finally if, which is an expression. Expression, if true is an expression, if false. We haven't completely flattened things here. And I mean, this is the same with let. We haven't completely flattened the binding. Yeah. Okay. Yeah, we have the bool. atomic. Okay. So we've updated, we have our Elm on if language. So add cases to RCO expression and RCO atom for the new features in elif. In recursively processing subexpressions, recall that you should invoke RCO atom when the output needs to be an atom, and invoke RCO expression when the output needs to be an expression. Regarding if, it is particularly important not to replace its condition with a temporary variable, because that would interfere with the generation of high-quality output in the explicate control path. So they're saying do not replace its condition with a temporary variable. So there should be an expression, a full expression in the condition of the if. Not just var or something. All right, let's have a look at remove complex operands. And I think that given the pattern that goes here, like this, it's removing this expression, not the entire thing into a variable. And like here, this, you know, was a no-op. Like it didn't transform any of this. Okay, so we are going to search and replace in this file, not in the whole project. Okay, so we're going to replace elmon var with elmon if, and we're going to replace elvar with elif. Okay, so now we should have some compiler errors. Yeah. We need to put a clause in here for because we need to handle if expressions. And we'll figure out what to do there in a minute. So down here, okay, we're given an elif expression. And we probably need to just add the missing patterns and we'll figure it out. Oh, that's interesting. This is a new feature of Gleam 1.11, by the way. The language server, when filling in patterns, will fill in the things for you if they're labeled like such. That'll be useful. So we don't have to necessarily do something like this. Okay, I'm going to move this up next to the other constants. So this is elmon if atomic bool value and counter. So this does not change the expression at all. I'll get some line breaks in here so I can see where the primary operations. And let's move, I think we have let up here. Yep, let's move this up under let because it's not a primitive. And then we can handle the other primitives down here. Okay, so what they're saying here is we kind of need to do like this and just, you know, recurse in covering each of these branches and then reconstruct it, right? So we'll do condition, call it C1, counter 1 is going to be RCO expression. So this has to do with the, like they're saying, don't make the condition atomic. You don't expect that to be atomic. It should be a full expression. I think that's what they were saying in the text there. So we will just pass this through. Counter 1. Counter 2. False. Counter 2. This is counter 3. Okay, and then we return elmon if C1, T1, F1, and counter 3. Okay, so we've implemented if. Now we need to go through here and deal with the, because these are primitive operations, right? We expect that they require atomic in the monadic if language. So we want atom is similar to the thing above, right? Bindings A, counter A. We'll do RCO atom of A counter. Let's just copy this because it's the same thing, right? And we say let new expression. We'll say bindings A, list append bindings B, list fold right, so this is our starting expression, right? So we do basically like this. And I remember this being like completely baffling to me. Or at least it required way more thought than I expected. And this is all on if let pair.0 pair.1 expression. Okay, so this recursively, not recursively, but it'll take, you know, we've turned this expression in here into an atom with a bunch of bindings to support that atom, and also this one is an atom with bindings to support that atom. And then we concat all the bindings and wrap them up from the right. So we're stuffing this primary operation inside a bunch of lets. That's what this fold right does. And then we return new expression and counter B. Okay, so I didn't need to retype that because it's basically the same. Oops. It's basically the same as the plus operation. Um, oh, interesting. Interesting problem here. If we have the shrink pass before remove complex operands, we never have to handle this case. And it's interesting because in the text, they're not saying anything about handling that case. So I think what we need to do is I think we need to panic here. And say panic as shrink pass not run before remove complex operands. Yeah, because remember we use this shrink pass to turn and an or into short circuit evaluating ifs, basically. So we don't need to handle that case. We need to panic if that case occurs. So I'm going to just have it ignore those variables, and then we'll move these up because these are the ones we care about. Okay, so here we basically need to do what we did for plus, but we do it for comp. And let's do comp and op. Okay. And then for not, we'll do very similarly. Actually, there's another, yeah, here it's like negate. So we will copy negates block and this will be not. Okay. So the shrink pass was not run before remove complex operands. So we should never have and or in this phase. And I would, you know, the other way that we could do it is say that this would be a little bit more overhead in terms of keeping track of things. But we could say that shrink actually outputs a different language. And it kind of does, but we didn't create new syntactic constructs for it. So we didn't create an elif shrunk, right? We just implemented it in the most straightforward way possible. Okay. Let's see. So remove complex operands has been updated. Let's see what else is wrong here. Okay. So in we need to handle if. We also need to handle bool. And I think that we probably need to put some cases in here like this in the atomic spot. right? Because we want to make sure that we don't get these inside atomic spots as well as inside of, expression spots. Okay, and the rule is basically any place you have an expression and you require an atomic, you need to bind it to something. And I think that we need to put bool here too. Right, because that's an atomic. This is a little bit dangerous, and I think I want to constrain it a bit more. We're going to do that, and then this will make sure that we don't miss any. Like it was a bit too open of a match there. Making sure that it's, this is a primitive expression, a primitive operation, means that we covered all of the branches without having a fallback to, I don't know what it is and I don't care. We want to make sure that we care there. If I had done that, let's say I undo that, now it says, hey, you're missing an expression, you're just not exhaustive, right? Should have done that to begin with. Okay, so we need to handle if. I think it really comes down to doing it like let. We've got to cover each of the expressions. Introduce a variable, bind that variable to the if, and return the counter. So, okay, so we got our work cut out for us. Let's do let C1 counter 1 RCO expression of C counter. And we'll do T1 counter 2 RCO expression of T, and that needs to be counter 1. E1 counter 3. We'll say, just to follow the pattern that's above, even though I'm not consistent in the other function, let's do this. The else. Okay, so that's the updated counter. And then we need to introduce a variable. So we need to do let, and this is counter 3. We'll say counter 3. Let var new counter is a new var of counter 3. And then we introduce a variable, var, and we return bindings of var binds to lmon if. And this takes C1, T1, and E1. And finally, new counter. Okay, so that wasn't too bad. It's just following the pattern that we had above. And remember, the idea of this is that we're replacing complicated expressions with let bindings, such that when you perform one of these primitive operations, your arguments are only variables or constants. So it's sort of like you're kind of unwinding the nested expressions, and preparing all your stuff and then doing the operation at the end. Okay. Our test is not going to compile anymore. We've got to do the same thing here that we did with Uniquify's test, right? So we're going to replace elmon var with elmon if. We're going to replace lvar with elif. And see if we have any compilation errors. All right, let's run these tests. First of all, I want to make sure that there's not anywhere else that we're referring to remove complex operands outside of this. Well, here, yeah, that's fine. And the test. Okay, so we do some in select instruction tests, but we already commented that out. Okay, so I think we're fine on other references to that. So let's run our tests. Okay, so I have a problem in here. Line 132. Okay, so the problem here is that those operators are basically the same type. We ran into this with x86. For now, I'm going to make a translator. We're going to say convert op, and this is going to take import eoc langs elif dot. We'll just import elif. This is going to take elif dot comp and give comp. And really it's case op, add missing patterns, and then it's just me like copy this. So this is dumb. We should probably have a common type there. But in the compile code, this is no op. If we, oh yeah, we need to fix that problem there. So let's do elmon if convert op. One thing I may or may not have shown before is if you look in the build directory and you look at the Erlang output, we can look at, let's see, right, so it has some intermediate stuff. Obviously there's the ebin, which has all the compiled modules in it. But if you look at in here, you get actually Erlang's source code. So we can look at, what was I wanting to show here? Oh, right. So if we look at elif, note that it doesn't have much in it. All the types have been turned into dialyzer types. So this is just comp here is atoms. The other thing that we could do potentially, and I actually like this idea a bit. Okay, so if we go like that's exactly what it is. There's no other construct in the emitted Erlang code for this thing. But if we go to elmonif, you'll see it produces the same thing. So these are, from Dialyzer's perspective, from Erlang's perspective, these are the same type, or they're equivalent types. They have different names, but they're equivalent types. And you'll note that the convert op does this. It's kind of superfluous. I don't know if the Erlang compiler will turn this into, the identity function. But it might. What might be better, let's ignore the compiler output for a second. I just thought that was interesting, and you should see it if you haven't already. What might be better is if, rather than redefining this type, we import it. And then in remove complex operands, that means we don't need this convert op. It's the same type. It will make some other things a little bit jank. Type. Okay. And then we'll get rid of this function, because that function doesn't do anything. And let's see if we can build. Okay, so we didn't introduce anything new. There's just warnings about unused modules. Not a big deal. Okay, so now we didn't have to convert that, and that's fine with me. Let's look at the test. Let's run the tests. No failures. Okay, so now let's come up with some new examples. Like this one should be a no op still. We introduced this order of bindings one, I think, because of a comment from the author of the book. And it was about the order operations of read. And I think that what we found out here is that, yeah, you want to evaluate left to right here. Depth first, left to right. So this read should happen first, and I think that we had an issue where one of them was getting reordered, and we would get this read happening before this one. But because they have side effects, you need to make sure that they happen in the right order. Okay, so let's cover. Let's make an example that covers if. There's not a way, as far as I know, there's not a way to test. Here, let me see. Should. There's no should panic. So we can't reasonably make a test that shows if you pass it a program with and or in it, it's going to blow up. But we can make something like if not less than read 10, right? And then we can, let's say 5. 42. Okay, so this particular program, what do we expect here? We expect not and an atomic. So we're going to get something like let temp.1 is going to be read, and then we're going to have another let temp.2 is going to be less than temp.1 10, right? And then that should be a Boolean expression suitable for this. So then we'll have if not temp.2 542, and you see here how we have and then we'll get the end of it. How we've made sure that all operations have atomic arguments. Okay, so let's implement this test. RCO if test. Not a great one. Okay, so we're gonna do we're gonna make a elif program, and it's gonna be if so not is going to contain an expression, and it's going to be elif comp it was less than is what I said. Okay. Primitive operation of read, and elif it was int is an expression, yeah, int 10. Okay, so there's our condition. Not, and this is incorrect because it needs to be elif.prim and so forth. This is getting really heavily nested. As we expected. Okay, so that's comp, and we need one more parenthesis for prim, and then prim and not. Okay, so there's our condition, and then we have int 5 int 42. Okay, so that type checks, correct syntax. So what we want is elmon if. So it's going to be, let's actually, no, we're gonna need different constructs here. So we'll be able to copy some of the things, but okay, so we actually don't have an if at the top level. We have a let, and this is going to be temp.1, and the expression is going to be elmon if prim read. And inside that, we're going to have another if, or another let. And we'll have temp.2. And that is going to be a primitive operation of comparison. And that's going to be, note that we reused the elif comparison operator. And this is a variable temp.1. Oops. And an int of 10. There's a problem here. Right, okay, that's fine. And then finally we have if, and we're going to do prim not temp.2. Yeah, note here that comp takes 2 atomics for its arguments, which is exactly what we wanted. Okay, so then we're going to do, this is an expression, so this takes an atomic. Int of 5 and int of 42. Okay, so now we're going to say P remove complex operands should equal P2. And yeah, I have no idea if this is going to work. We'll find out. Let's run it. Okay, so interestingly, what did we get that was different? So we didn't, I think that what I was expecting is this to possibly be what explicate control does. And I don't think, yeah, see, in this example, you can have lets inside of lets. It's not fully flattened. So the question is this correct? I think it's fine, actually. So what we're going to get here is right, you don't get a full unwinding of this because this is not a complex operation. So we do get 2 variables introduced. Yeah, I think that this is correct, and it's not fully, because like this is explicitly like the order that you would want for translation into the C-like language, but we're not at that point yet. We're just simplifying complicated operations into simple operations with bindings. And then the explicate control phase will pull out this stuff. So Yeah. Okay. So let's look back at this, and I need to readjust my expectations. So we actually have if let temp.to let, and I'm not consistent with my stuff there, temp.1 is read and this is less than temp.1 10. And then once we have the temp.to binding, we can say not temp.to. That's what this is. And then that becomes the condition. And then we have 5 or 42. That's interesting. Let's look at these other things. Right, this is a really simple example. But note that it's only concerned with things that require atomic arguments. Like if this actually follows, the output that we got here actually follows the pattern of, yeah, the condition can be an expression. It doesn't need to be atomic. In fact, here we were expecting it to not be atomic, but all the bindings to flow to the outside, and they didn't. So I think this is fine. This is correct. So let's honestly let's redo the whole program. And I hate to retype all that, but what we want is the if at the top level. Okay, so we want the if at the top level, and what we need to do is replace the condition with our with this expression here. So let's make the let, and this is going to be temp.to. And that makes sense because remember it's doing depth first, so this binding here gets created first, and then temp2 is created later in the traversal. Okay, so we have temp.to is assigned the value of another let. This is temp.1, and that gets the value of read. And then we do, and you know, I could just copy what it says in the terminal, but I'm not going to. Even though my typing sucks. We're in 10. Okay, so then, right, so that binding, then you evaluate not of okay. All right, let's run this test again. Okay, so we got the correct answer this time. And we didn't look at the output too much from the previous failed test. So I feel pretty good about that. And I guess this makes sense. What would happen, or or what is going to happen in the explicate control pass is probably that, because that, if you remember, turns the monadic form into the C form. Right, so this one was like explicit execution order, so a graph with gotos essentially. That's turning this let thing into some assignments. Yep. Okay. So, let's go ahead and add those. Look at the diffs. This is chapter 4.7, correct? Yeah. Update. Remove complex operands for elif. Okay. There's a bit of this is feeling a little messy, but I think that we should strive forward, and let's look at explicate control. All right, so recall the purpose of explicate control is to make the order of evaluation explicit in the syntax of the program. With the addition of if, this becomes more interesting. The explicate control pass translates from elif to cif. So we defined cif last time, right? It has, in addition to the return and sequence that we had before, it has goto, which jumps to a new label, or jumps to a specific label, and if, which is like, do the comparison between these two things, and if it's true, jump to this label. If it's false, jump to that label. Okay. Now they say that, like, we'll leave this goto in here. I was thinking, oh geez, do we actually need this? Because if we have, when we have if in this, this is actually a goto and this is actually a goto. Okay. Okay, so make the order of evaluation explicit in the syntax. With the addition of if, this becomes more interesting. The explicate control pass translates from elif to cif. Oh yeah, so the other goto is when both of them are done, you may have a shared tail expression, and you want to jump to the continuation of that, right? That's why we left goto in there as an explicit thing. Okay. Okay, the main challenge to overcome is that the condition of an if can be an arbitrary expression in elif, whereas in cif, the condition must be a comparison. Okay, so we'll probably want to take advantage of this motivating example here in our tests. As a motivating example, consider the following program that has an if expression nested in the condition of another if. Hold on. Did we, in our test here, was it this one? Did we commented a bunch out? No, it was in the select instructions. Okay. We'll skip over that until we get to it. Okay. The naive way to compile if and the comparison operations would be to handle each of them in isolation regardless of context. Each comparison would be translated into a comp queue instruction followed by several instructions to move the result from the eFlags register into a general purpose register or stack location. Each if would be translated into a comp queue instruction followed by a conditional jump. The generated code for the inner if would, in this example, would be, so they're talking about this one. Would be as follows. Compare 1 to x set L of AL, and then move it into this temp location. Compare compq1 temp and jump, then branch 1, else branch. Jump if equal, then branch 1. Okay. Notice that the 3 instructions starting with set are redundant, right? Because you've already compared this. The conditional jump could come immediately after the first compq. Our goal is to compile if expressions so that the relevant comparison instruction appears directly before the conditional jump. For example, we want to generate the following code for the inner if. compq1 of x, right? So jump less than, then branch. Jump, else branch. So that's an unconditional jump, right? One way to achieve this goal is to reorganize the code at the level of elif, pushing the outer if inside the inner one, yielding the following code. Right, so this is like they're saying do this, put this condition in here. Let's see here. Okay, so you've already got let x read, let y read. If x is less than 1, okay, so they're like distributing the if over each of those branches because we know that this expression, this original if expression returns a Boolean, right? Okay, so whatever the contents of that condition are, regardless of what's inside, those have to be Booleans. And so they're extracting the if true branch and the if else branch and making those conditions of the other ifs. Okay, so unfortunately this approach duplicates the 2 branches from the outer if, and a compiler must never duplicate code. After all, the 2 branches could be very large expressions. How can we apply this transformation without duplicating code? In other words, how can 2 different parts of the program refer to one piece of code? The answer is we must move away from abstract syntax trees and instead use graphs. At the level x86 assembly, this is straightforward because we can label the code for each branch and insert jumps in the places that need to execute the branch. In this way, jump instructions are the edges in the graph, it makes sense, and the basic blocks are the nodes. Likewise, our language cif provides the ability to label a sequence of statements and to jump to a label via goto. So, without going forward reading more of this, what I'm guessing here is that we will basically rewrite the explicate control. It's not going to be a little patch like it has been so far. And honestly, in the original, it was the most complicated pass, I think. Select instruction wasn't hard. Patching instruction wasn't hard. Generate, prelude, and conclusion weren't hard. But explicate controls the meat of it, and it was complicated. Okay. As a preview of what explicate control will do, figure 4.12, yeah, we'll go look at that in a second, shows the output of it on this example. Note how the condition of every if is a comparison operation, and that we have not duplicated any code, but instead used labels and goto to enable sharing of the code. Okay, and recall that in section 2.6 we implement explicate control for lvar using 2 recursive functions, explicate tail and explicate assign. The former function translate expressions in tail position, with the latter translate expressions on the right hand side of a let. Okay. With the addition of if expression, to elif, we have a new kind of position to deal with, the predicate position of the if. We need another function, explicate pred, that decides how to compile an if by analyzing its condition. So explicate pred takes an elif expression and two cif tails for the then branch and the else branch, and outputs a tail. Okay, so let's look at their example here. They're saying, so let x read, let y read, and the if plus y2. Okay, so they go, x is read, y is read. If x is less than 1, go to block 4. Else, go to block 5. So if x is less than 1, we would expect if equals 0, right. Okay. So they're saying they're allocating labels, block 2, block 3, so forth, for the if branch. Okay, if equal x0, go to block 2, and there's a return there. Else, go to block 3, and there's a return there. Okay. So I think what's interesting there is that, they were discussing that in the paragraph on the previous page. They're allocating the then and else blocks and saying, because the contents of this expression have to be a Boolean. If there's, in this case, there is an if in here. So it's kind of like what we did in some of the other passes, like you're injecting the destination, like almost like continuation passing, but not exactly. So they're saying, we're going to allocate block 2 and block 3, referring to these two branches of the if. And then however this evaluates, it's going to decide, if it's a simple one, it could be it would put the jumps in there. Right, and this is the inner expression. So it's kind of like you're evaluating the inner expression first. Right? So it's kind of like here's your tail for this if, and that those tails get, this is going to be kind of wild, I think. I'll get my brain wrapped around it, and hopefully you'll be able to follow along. We have about 25 minutes left. Okay. So we know in here we're going to need, first of all, we need to do our search and replace. We're going to replace C var with cif. Okay, and we're going to replace lmon var with lmon if. And now we're going to have compiler errors. And we will figure this out. Okay. So this is going from lmon if to cif. All right, already we need a few things in here. So we're going to have to think about how to update these. Okay, so the explicate tail and explicate assign functions need additional cases for Boolean constants and if. The cases for if should recursively compile the two branches using either explicate tail or explicate assign. Obviously, in here, it needs to be, what did we figure out? Right, it needs to be explicate assign. And then the cases should then invoke explicate predicate on the condition expression, passing in the generated code for the two branches. For example, consider the following program with if and tail position. Two branches are recursively compiled to return statements. So let x is read if x equals 0. So this would be return 42, return 777. We then delegate to explicate predicate, passing the condition equal x0 and the two return statements. Okay, so tail position, I think we can cover easily based on this. So we're going to have to make, let's make a function explicate pred, and so we need the generated code for the two branches. So we're going to need okay, I think that this is going to be, there's an interesting problem here in that what is the problem? The problem is that we need to compile they're saying it needs to be passed the generated code for the two branches. But is the generated code a tail? Or could it be a statement? I think it needs to be a tail because even if it has a statement in it, you're likely to have assign and then a go to. Okay, so I think that kind of convinces me. This is going to take the condition is going to be elmon if expression. No. yeah, it's going to be an expression. And we're going to take, you will say if true, just like we did for other things. This is going to be a cif tail. If false is going to be cif tail for now. And I think that what this what it should return is a cif tail, and we're just gonna put to do in here. I'm not fully convinced of that, but let's try this and see what we get. Okay, so the two branches are recursively compiled to return statements. So regardless of what's in that branch, it's going to be a return at the end if you're in tail position. For those, because there's some sequence of things, and then because this if is in tail position, these are also in tail position. Okay, so when we're handling, let's go here. Let's add the missing patterns. Okay, so we're gonna have to I want to move this up. We need to handle these other cases. Let's leave this one as a to-do for now. I think because what does cif have? Okay, so it can return an expression, which is a primitive operation. Okay, so we can do comp, right? I'll label that for funsies. Okay, so here, what we want to do is, yeah, return takes an expression. So this should be cif return, because we're in tail position. We want cif comp. And we're going to need to translate that op. Honestly, at this point, I'm like, hey, we should have a shared module for all these operations, because they're all the same. All these comparison operators. Yeah, I'm just going to import that. We're going to do import EOC langs elif comp type comp, right? Then we don't have to translate it. It's the same operator. Okay, so we return op, and that's an atomic. What do we do with other atomics? We call convert atom, okay? And convert atom B. Okay, we need to wrap that in a prim. Okay, so that one is handled. We need to add a case to this. Okay. And then we need to implement not. So that's should be fairly straightforward. We're going to return. Okay. So now explicate tail for right. So we do explicate tail on if true and if false, and then we call explicate condition or explicate pred with the condition expression. Yeah. So we're going to do let T1 is explicate tail if true, explicate tail if false, and then we're going to return explicate pred of condition T1. Well, we want to call it F1, F1. Okay, so I think that's what they're saying here. Right, so we recursively compile them to return statements. So saying, essentially they're saying, that's a tail expression, that's also a tail expression, because this if is in tail position. And then you call explicate pred, passing the condition that was given, and the two return statements. Okay. So now we need to talk about if it's in assign position. So first, before we go forward, I'm going to add the missing patterns there so it stops looking so red, and then we'll figure it out. And these can move above the let because they're simpler. Okay. Okay, so an if on the right-hand side of a let. Note that the body of the inner let will have already been compiled to return, plus x2, and passed as the continuation parameter of explicate is signed. So we'll need to use cont to recursively process both branches of the if, and we do not want to duplicate code, so we're going to generate the following block using auxiliary function create block. Okay, so we're going to have a function create block, and I don't know what it does. Discussed in the next section. We then use goTo block 6 as the continuation argument for compiling the branches. Okay, so the branches compile to x equals 40, go to block 6, x equals 77, go to block 6. Finally, we delegate to explicate pred, passing the condition and the previously presented code for the branches. Explicate assign does return a tail. So we're fine calling explicate pred here, right? They're saying using a global variable. We won't be able to do that. We're going to have to thread a dictionary of labels to tail expressions through, and that's going to make it a little bit messy. So we might want to make a not just an auxiliary function, but an auxiliary module even. You know, we had the graph for allocating registers. might need to do something like that. Right, and here's where it's introducing goTo. Right, and then so what they're doing here is they're saying, if you've got a goTo, just return the goTo. Otherwise, generate a symbol. That's where they're getting this block 6. We're going to have to do that manually. Carding around the counter. Let's do right, okay. Let's do type blocks. Is going to be blocks, and it's going to be counter. It's going to be an integer, and then we're going to have that's just going to be keeping track of our the blocks that we have, like the max that we have created. And then we're going to have to keep a dictionary of, this is going to be a string to tail, right? Yeah, it's just saying it's not used. Okay, so we're going to say new blocks, and this is going to return blocks. I'm going to say blocks 0 and dictionary. The other thing that we could do here is use the dictionary's length to pick the next identifier. That would probably be okay. And let's just make it an alias, like so. And then we'll say, yeah, this is just dix.new. And then create block is going to take it's going to take the existing blocks, and it's going to take a tail expression, and it's going to return a tuple of blocks and a new tail expression, right? Okay, so then we can do this, and we'll say case tail, and we're going to say if it's a goTo, we're going to return tail. We're going to return blocks and tail. So basically, if it's a goTo, right. If it's anything else, then we're going to put this tail expression into the dictionary, generating a new label. So we're going to say new label is dict.size of blocks +1 +1 new index. And we'll say new label is right, okay. We're going to say how did I do this before? We've done this in like we didn't remove complex operands. We generated a new var. Okay, so let's do that. And since we're going to insert it into the dictionary, we don't need to keep it around. I think that was my first instinct was, oh, keep the counter, but you don't need it. And we're going to say this is block underscore concatenated with that. And then we will say what we're going to return is inserting new label, or inserting into blocks, new label, and tail. And the replacement is goto of new label. Okay, so we basically implemented the same. We need to import Gleam. We've implemented the same create block that they did. I'm going to remove this. We're only using it internally. Okay, so then up here, what we need to do is we need to start passing this through. And this is going to be, these are the blocks that we have existing, right? And we need to do that into assign as well. And so everywhere we're calling explicate tail or explicate assign, we need to pass the blocks. And I think explicate pred might need it as well. We'll find out. Okay, an explicate assign. This might be interesting. We haven't handled this stuff yet. Let's go ahead and pass blocks in here. And I don't know. The interesting thing here is, will there need to be new blocks created inside this let? I don't know the answer to that yet. Okay, so in assignment position, I think we can handle comp and not right now. And then we can go back and look at if, which is probably going to have to call an explicate pred. So, all right. So this will be cif. So we're having a sequence. Right? Cf assign the variable comp op convert atom A convert atom B. That's pretty straightforward. And then the continuation. Okay, we need cf primitive operation. Okay. And then this will be basically the same thing. This is following the pattern of all of our stuff that we've done before. So it's v, this is v equals a op of b, right? And then the continuation. And this is going to be v is not value. We'll use C syntax there. So it's going to be basically the same. It's a sequence. cif.sequence. And we're going to assign v cf primitive cf not convert atom value and continuation. Okay, so that covers everything here except for whatever elmon if needs to do. So let's go back up here. So in explicate assign, we'll need to use cont to recursively the continuation to recursively process both branches of the if. So we'll generate a block using an auxiliary function and create block. Okay, so this is interesting. We'll need to use the continuation to recursively process both branches of the if. Okay, so this if is in assignment position. Right, okay, so, and so the next is, it's like this stuff, right? Right, so you said v1 this is the stuff that broke my brain last time we worked on this. Okay, so we want to, right, so this is an expression. You want to assign that expression to a variable, v1. And then you want to assign the value of the let to the variable that was requested. So this is a let in assignment position. This is actually not what we're dealing with. But we can kind of think of it like that. So actually if we go up here and we say, let's assume there's a let. We have explicated the tail here, E. And then we're saying E is the this new tail is the continuation. And we want to assign whatever expression is in B to V. I wish I hadn't switched those. That's okay. And these are the blocks that we have already. Okay, so here's the other issue, I think, which is that explicate assign can return new blocks. We don't have global variables, but we want to keep track of all the blocks that we created, right? So explicate tail needs to return the new tail. This is the tail of the start function plus any modified blocks. So this means that we actually need the blocks here are, we already have this definition essentially. The CIF program right? It already has this type. So we should put that type over there and use it. And this is going to be just blocks. Now the compiler probably, the Gleam compiler would probably be fine. It'd be like, yeah, you know, those are actually the same type, even though you've named them different. But in this case, we need to right. So actually, rather than from list here, what we're going to do is we're going to dict insert into blocks, start, and the new tail. So we're going to have to, in each of these cases, return tuples. Here we didn't modify the blocks. And that way we can collect all of the new blocks that are generated by folding over this syntax tree. New blocks, right? New blocks. And then we'll need to make sure that explicate assign also returns this same type. So that's going to be fun. Let's fix all of these clauses first, and then we'll say this is going to take blocks, this is going to take B1, and then I don't know if this will modify the blocks yet, so let's just assume it does, but it's going to have to take them, right? And here, you know, we're not modifying the blocks. Same here. We really only need this when we're introducing jumps, go-tos. So that'll be in let and if are the only places that may introduce go-tos. Okay, so now we need this type here, and we're not modifying that on an atomic value. We're not modifying it on any of the primitive operations, right? This is a thing that, like, you know, it's a little bit messy to use global variables for that sort of thing, but otherwise you get into the situation where you need to create types that for each of these operations contains, you know, the modified stuff. Like we had this thing is immutable, right? So here we're going to go that's an interesting question here. I think this is correct. I had inlined it before because we didn't have to pass the blocks through, but I don't see a way that it would make sense to evaluate this continuation first. It doesn't really matter, honestly, who creates what blocks. Okay, so let's think about this if in assignment position. Okay, so we're essentially, what we want to create is let's just say block 1 is continuation, right? And then we're creating okay, we need to update explicate pred and blocks cf.blocks. Okay, we don't know what's in this function yet still. And it's going to have to return blocks because of our threading through, right? Okay, now that warning went away. Okay, so what we're going to have is we take the continuation and we make a new block for it, right? And then that becomes the continuation. That goto becomes the continuation for both of those. All right. So we're going to do I want to reverse this so it's a bit more consistent. This is going to be tail and blocks. And I'm going to reverse the arguments as well, because then it'll be more consistent with the other functions that, except we need to reverse that. Okay. CF. Okay, so then this looks like kind of calling explicate pred, explicate tail, explicate assign. So we want we're going to say new continuation, new blocks is going to be create a block for the continuation with the existing blocks we were passed in. Okay, so that's step 1. So like conceivably it'll create like block 6 return plus x2. Okay. So then we need to do explicate assign on each of these. Because whatever the value of these expressions, whatever the value of these expressions are, should be assigned to the variable. And then their continuation is to jump to whatever the expression was that was after this, because this is not in tail position. So whatever the expression was after this if. Okay, so let's, and I've gone over again, but I feel like I'm close to understanding. So I would like to continue. Okay, so what we're going to do now is we're going to say we want a new true branch and new blocks. We're going to do explicate assign, and so here we're doing a variable. So this is the variable, right? Is that correct? No, it's expression comes first. Okay, so we're going to pass if true variable, right? And the continuation is the new continuation and new blocks. Okay, and then we're going to do F1 B2, and we'll explicate assign on that as well, the if false branch. Also assigning a variable, and the new continuation is the same, but now we have new blocks potentially. Finally, we delegate to explicate predicate, pass in the condition. Okay, so now we call explicate pred, and that takes the condition, and it takes the transformed if true, if false, and the new blocks. Okay, so that makes sense. Excuse me, B2. So we're saying we know that after each of these is done, they need to jump to the expression that follows the assignment. And so we create the block that captures that, and then we treat them both as if they are assignment expressions, and then we handle the predicate. Okay. So there's create block. So now the skeleton for explicate pred is given in 4.13. Takes three parameters: the condition expression, then the code generated by explicate for the then branch, else the code generated for the else branch, and of course we also have the blocks. They were treating the blocks as global, and then but yeah, okay. So we need to, let's outline this. So we're going to say case condition, and we need to handle variables. Variables lets not other ops. Okay, create block. So honestly though, with our version of ifs, we are expecting them to always be labels. So that's going to be interesting. It's okay. We can possibly match on this. The other thing that we could do from create block is return the label. So, okay. All right, I want to go for just a few more minutes and then we'll wrap up. Okay, so we have let's just let it fill out all the patterns and then we'll expand some of them. Okay, so they are handling some explicit things. So var being an atomic, we need to be like they have an explicit case for that. And what I want to let's add the missing patterns. Yeah, so we need to handle vars. We need to handle let. We need to handle some primitive operations. So let's make this one explicit. They explicitly handle not. Interesting when they say equal or less than. Why would they bother with less than? Right, so I don't know why they had that predicate on there. All right, well, let's handle the not case. Okay, and then we're going to have to handle all these others. So, comp is fine. These others should be invalid. These should be... Oh no, bool needs to be in there. Let's move it up to the top so it's there. Ints are not valid here. So let's say other, we'll say panic, unexpected expression in condition. I think that covers all of the cases that they're showing there. I don't know why they had this when. We'll figure this out. maybe we'll say this just to be parallel to what they said. And I'll use the match anything pattern there. So these patterns we're explicitly not handling. Okay, so I'll just have it in the same order they do. Don't really like that. I kind of like having the same variants next to each other, but we'll see. Okay, we're going to read a little bit more, and then I'm going to wrap up for the day. Maybe we can finish or get a lot of this done, and we can complete this phase next week. Okay, so they're talking about consider the case for comparison operators. We translate the comparison to an if statement whose branches are go-to statements, created by applying create block to then and else parameters. Okay, so they're talking about this, the comp operator, right? So we're going to do okay, let's illustrate this translation by returning to the program with an if expression and tail positions shown next. Okay, we invoke explicate pred on its condition. So this is let x read if equals 0 x, if x is equal to 0, 42, otherwise 777. Okay. The two branches 42 and 777 were already compiled to return statements. That's what we did before here. From which we now create the following blocks. Okay. So let's say we're going to say we'll call it A branch. Or no, we'll call it then block. And B1 is create block for the if true, right? With the existing blocks. And then we say else block to create blocks. So we're creating blocks for each of these. If false, blocks. And then okay, after that, explicate pred compiles the comparison to the following if statement. So yeah, this is where I think the create block should probably return the identifier directly. And I understand why in the text they are, let's see, where are we calling create block? Okay, so we do it here in if, right? I wonder if we can get around that. We can change cif. It's a little bit less strict, right? But this can be a tail and this can be a tail. And then we have the go-to directly. It's just I wanted to make sure that, because based on what they were saying earlier, that these were always going to be go-tos. Let's change it to tail, and that'll simplify our code here. I don't think that it's absolutely necessary to do this like that. Okay, explicate pred compiles the comparison to the following statement, if statement. Okay, so then we're going to say this needs to return the updated blocks and a tail expression. So we're going to return if, right? No, we're going to return cif and it's going to take op, right? Because those are the same type. Do op like that. We're going to do A and B if true, if false. Okay. So A is going to be convert atomic of A. B is going to be convert atomic of B. And then the if true and if false are going to be then block. If false is going to be else block. And I could have been more consistent with the naming here, but and then finally, so after that's the tail expression, and then we need to return the updated blocks. So okay. All right, so that's what they've outlined for us there, is basically like do this, primitive operation. Now we have exploded this to keep the type consistent. We could turn it into, this needs a primitive operation, or it's just a, what is the word? It's just an expression, and we happen to be prim right there. That might be worth it. So honestly, let's put that back into here. Let's rename this. This is the condition, and it needs to be expression. And let's go, I was uncertain about it last time when we were defining this language. It's like, we need to be stricter on this. But in this case, I think we're actually going to be fine if we do cif prim. And that's going to take cif comp. And let's take op, convert atom A, convert atomic B, and then we do like so. I need a comma there. Okay, so that parallels what they have here. I'm not sure what this guard is for. Let's try to read, see how much longer this section is. Let's try to read up to 4.8.4 and see if we can finish this up. So, okay, next consider a case for Boolean constants. We perform a kind of partial evaluation and output either the n or the else parameter depending on whether the constant is true or false. That makes sense. So it's a little bit of an optimization there. Let us illustrate this with the following program. So it's not a separate optimization, it's just part of this. Okay. So we can do case value true. So if we have if true 42,777, and there's compiled to return statements, it obviously doesn't matter which one they were compiled to. So it compiles the constant t to the code for the then branch. Okay, so if we have a constant there, we do we don't create any new blocks. This is going to return the if true branch. and blocks. If it's false, it returns the if false branch and blocks. That's straightforward enough. This case demonstrates that we sometimes discard blocks that are input to explicate pred. That's fine. The case for if expressions is particularly illuminating because it deals with the challenges discussed previously regarding nested if expressions. So these inherit their context from the current one, that is predicate context. So you should recursively apply explicate pred to then and else branches. For both of those recursive calls, pass then and else as the extra parameters. Oh, right. So figure 4.12 shows the output of remove complex operands pass and then explicate control pass on the example program. We walk through the output program. 4.12. Okay. Okay, so we still need to handle these other cases. We need to handle let. We need to hand, so this the recursive if, I think it's like, this is one of the examples that they were giving here in that figure. This needs to be B1. I need to thread that through. First have two calls to read and then a comparison in the predicate of the inner if. In the output of explicate control, in the block labeled start, two assignment statements are followed by an if statement that branches to block 4 or block 5. The blocks associated with those labels contain the translations of equal x0 or equal x2. In particular, we start block 4 with the comparison equal x0 and then branch to block 2 or 3, which correspond to the two branches of the outer if. The story, okay. So it's like, so when the if is in the condition position, that's what we're testing here. That means that these branches have to return Boolean expressions. Or they are Boolean expressions. And this condition This is sort of like the explicate assign with the lets. I'm going to get my brain broken by it because it's kind of a recursive condition, a recursive like operation that we need to handle. So it's like you evaluate, your goal is evaluate this condition and branch to either of these, jump to either of these based on the value of this condition, and then whether this is true or false, you branch back to the original ones. Okay, so I think what this is saying is, yeah. So we'll say these need to get new. We'll call it C inner, T inner, F inner. So we need to we're going to do explicate predicate. This is going to be on we're going to treat if true, right, as the condition, or rather T inner, right? And then it's going to branch to if true and if false with blocks. And then we'll do let F1 B2 is we're going to do the same for the false branch, the else branch, and this will be B1, so we keep accumulating the new blocks. Okay, so we evaluate each of these as if they're going to follow up with those tails. Actually, this is wrong. So let's do this, because I think that we need to make it possible to jump to these tails and not duplicate them, right? So this is then block, else block, and here we're going to do B3, B4, and this is B2, then block, else block, and this would take B3. Okay, so we have to create blocks for the destination branches so that both of the potential predicates can jump to those, and then here's where we construct the thing at the end. So we'll do an if actually, what do we do? I think we call explicate pred again, because now we want to evaluate the condition for this if, and its if true is T1 and F1 and then B4. Yeah. So, okay. So this is C inner. Right. So because we need to like the order of operations is, you do the inner if first, and then it branches to one of these Boolean expressions, which they do their evaluation, and then they branch back to the original true or false branches because they are Boolean expressions, right? So, whew. I think it's a good place to stop. We still need to handle let and atomic variables and so forth. We will get to that next time, I think, through the rest of their explanation, and we can we can finish this up. So this is a good place to stop. Thank you for bearing with me for the extra time, and we'll see you next week, I hope. Bye.